Hello everyone, we're going to start our next packet, Introduction to Stoichiometry. Good chemistry word there, stoichiometry. Okay, it means to balance. So you've probably done a balanced chemical equation before, and we're going to come back and look at that first one as a simple example, and we kind of combine carbon and oxygen to make carbon dioxide right in that first packet. That's the kind of thing we're talking about. So how to balance an equation, okay? Now, balancing equations comes right out of Dalton's atomic theory, okay? Particularly number 3, if you look at his postulates, right? So atoms are not changed into different types of atoms, so you can't have alchemy, right? You can't turn lead into gold. And maybe I didn't stress this enough the first time we looked at it, atoms can't be created or destroyed. So I did think I mentioned, the universe is like a box of Legos, 119 different kinds of atoms, right? 119 different kinds of Legos, if you like, in different amounts. And then we just stick them together to make elements and compounds. All right, so there's a fixed number of hydrogen atoms in the universe. There's a fixed number of gold atoms in the universe. That's kind of why gold's expensive, because there's not much of it, right? So the expensive things, supply and demand, right? There's not many of them, okay? Hydrogen's dirt cheap because it's everywhere. 99% of the universe is hydrogen, all right? So bottom line is, when we do a chemical reaction, we can't change atoms from one kind to another. And, feel free to kind of make little notes down here as I talk, right? So this is kind of what this space is for. Okay, so you can't turn one kind of atom into another, okay, and you can't make them appear or disappear, so they can't be created or destroyed, okay. So when we do a balanced chemical equation, we have to have the same number and type of atoms we start with as the same number and type we finish with, and that's the essence of every balanced chemical equation, obeying what's called the conservation of mass law, which means, hey, same number and type of atoms before you start, same number and type after. We didn't make any disappear, we didn't make any appear, they didn't change identity. And that's basically what balancing is. All right, and then, Dalton, just a little catch up here. Dalton did say, of course, that, when we make a compound, it has a fixed ratio of atoms inside, H2O, 2 H's, and an O. Okay, all right, so stoichiometry or balancing is the relationship among the quantities of reactants and products involved in a chemical reaction. All right, now if you remember, for our, some of our very first reactions, and I said, hey, let's go to nature's subway and make water. Take a hydrogen, and an oxygen. Oh, let me move it up so you can see it perhaps. Okay. Take a hydrogen atom, and an oxygen atom. Stick them together. They stick together to make H2O, right? Remember, that's kind of like a jelly bean type thing, right? Once it's formed. Now, unfortunately, we can't do that when we do our balanced chemical equations, which would be H plus O, because atoms don't exist by themselves in nature unless they're noble gases, and that's a catch-22 because noble gases don't react. So, for example, hydrogen is in the form H2, right? So diatomic. Oxygen's in the form H2. So we have to use, molecules, and if it's a giant element, different formulas as they are, as we find them in nature, okay? So we don't find hydrogen as single atoms, we find it as H2. So we have to use H2 when we do these balanced equations, all right? So, we can't do a simple atom with atom combination. We have to kind of think about what they are in nature. Okay, so moving on, switch over the page here. Okay, so remember, we mentioned it before when we talked about this very reaction right here. We'll go through this in a little bit more detail. Okay, remember, the goal of any chemist is to explain a macroscopic event, like, for example, the burning of charcoal, in terms of the repeated identical reactions of the particles involved, okay? So a single atom of carbon in that brick of charcoal reacts with a molecule, O2, of oxygen from the air to make a carbon dioxide molecule, okay? So that's the one-time event. Remember, that's one, I kind of embellish this a little bit. Remember, that was the one carbon atom in the block which reacted with a molecule of oxygen to make CO2, right? And that just repeats many billions of times over to burn a big old chunk of charcoal, okay? So that's what balanced chemical equations are. A single one-time event on the microscopic level that repeats many times to describe a macroscopic, a large-scale event. Okay, all right. Now, if we dissect that equation, one we saw before, what does this mean? That's a single atom of carbon, as we mentioned, right? That's a reactant. So things on the left side are things we start with, right? So a single atom of carbon, yes, solid inside a larger brick, right? So we're concentrating on one atom, But it's not just one atom sitting there, is there? There's trillions, right? So one out of those trillions is this one, right? So that kind of solid says, hey, it's with its friends, but we're just concentrating on you, right? So there it is, nice picture. All right, so one carbon atom, single atom of carbon, reacts with, or bumps into, reacts with, adds to O2, right? So that's an O2 molecule. There's a nice kind of geography map, a structural formula of O2. Remember, red for oxygen. Okay, this is important. Turns into, so one-way street, right? So it's a single-headed arrow. These things turn into and don't come back from here to here. They turn into CO2, right? So it's a carbon with an oxygen stuck each side. Obviously, when we do a formula, carbon first, oxygen second, because of the way we name things, right? And where we put formulas together. But that's what it looks like in nature. It's a carbon kind of stuck with oxygen each side. Okay, so turns into, goes to is the arrow. Okay, products, these things are what you make, products, right? So that's a single molecule of carbon dioxide as a product. So that's our first chemical equation that was balanced, all right? So we're going to learn how to balance these equations just like we did before, okay? You'll notice it obeys Dalton's law, right? Nothing was created or destroyed. We've got one carbon before or one carbon afterwards. Two oxygens before, two oxygens afterwards. Yes, they've swapped partners. That's chemistry, right? Kind of dismantling, if you have a bunch of Legos, you kind of build a tower, you dismantle it, and then maybe you put them back together and build a boat, right? Okay, that's exactly what you do here. So it's the same number and type of Legos, they're just rearranged differently. So that's what chemistry is, changing the bonding of a fixed number of atoms to go from reactants to products. Okay, so we always see the same number and type of atoms before and afterwards. You can't create or destroy. Okay, now, so before we get into the nuts and bolts of balancing, we need to talk about the types of reaction you're going to see. Okay, so let me kind of give you an analogy. When I think about cars on the road, or vehicles, to be better, right? So there's literally, let's think about it, there's 250 million people in the United States approximately, and we average about 2 cars each if we include work cars, etc. Okay, so there's probably 500 million vehicles on the roads in the United States. Okay, every one of them is in some way different. And that's a lot like reactions. There's probably a similar number of chemical reactions in nature, and they're all slightly different, right? Okay, so there's, lots of different reactions. However, when you think about vehicles on the road, there's only really 5 types of vehicles. There's pickup trucks, there's like regular cars, there's minivans, right? So it's probably 5 kinds of vehicle. And in the same way as there are 5 kinds of vehicles, but like almost infinite kind of examples within each type, same thing with reaction. So there are 5 kinds of reaction, each with many, many thousands or even millions of examples, okay? All right, so let's talk you through the 5 simple types of reaction. Okay, now combination, that's the word, right? Combination, you stick things together, a combination of things, right? Combine, right? So combination, you start with more, here's a generic, you start with more things and end with less things. That's a combination. So if you look on the left of reaction, and our first example was a combination. So I start with 2 things, an atom of carbon, an oxygen, and a molecule. That's 2 things, right? Stick them together to make 1 thing. So that's a combination, okay? Now, because you can add oxygen to pretty much everything, that's called combustion, right? So combustion is like a special, very common type of combination, okay? So anytime you burn something, it's a combination. If you want to be specific, it's a combustion, okay? So on the test, you can say either combination or combustion if I said, hey, what type of reaction is that? Okay, fair enough. Now, and there's a generic. A plus Z makes AZ. 2 things stick together. Okay. Now, the reverse of a combination, it's not decombination, but it sounds like it. It's decomposition, all right? Now, decomposition is when a large unstable thing falls apart to make more things, okay? So think of being in a restaurant, all right? And a waiter walks past your table with a tray with 16 drinks on it, right? Very large, unstable collection of matter, right? You nudge the waiter and suddenly you got a pissed off waiter and 16 drinks on the floor. So something that was large and unstable, 1 thing, turned into 17 things, 16 drinks on the floor and a pissed off waiter, right? Okay. So it's a truism in nature that large, unstable things will fall apart to make smaller, more stable things. More on this in the next packet, but basically nature likes small, unstable, right? So in this particular case here, calcium carbonate, calcium, if you remember, is a small +2 ion, and carbonate's a large molecular ion. Nature doesn't like that size difference, so it makes them fall apart to make smaller things, okay? So calcium oxide and CO2, all right? I'm not combusting, right? If you notice, I'm not adding oxygen here. I'm just shaking it with energy. So you can heat up baking soda. You don't burn it. It falls apart to make carbon dioxide when you make soda bread, right? Similarly, if you heat up chalk, and oftentimes you'll see a little delta there for change, right? If I heat up some chalk, I'm not burning it. There's no oxygen over here. I'm just heating this thing up. I'm shaking it with thermal energy, right? It falls apart to make two smaller, more stable things. So that's a decomposition. If you see more things coming from less things, it's kind of the reverse of a combination. That's decomposition. All right, so I kind of think of them as the reverses of a combination. Now, next one. The next couple, I've given you some kind of weird analogies to help you remember. Okay, so you may be asking yourself, why is he showing me all these little weird pictures all the time? Because if you can make an association with a kind of a weird, kind of hard to remember fact with something weird, like a picture or something, it's easy to remember. So that's why I kind of flash up pictures occasionally, so it helps you remember. All right. So here, hopefully you remember single replacement. I call a single replacement a prom reaction, okay, a prom reaction. Why? Well, you know, my experience of proms is minimal because I'm from England. We don't have proms. Okay. All right. So, you know, all my expertise comes from watching movies like 16 Candles and Pretty in Pink. You know, these movies, coming of age movies from the 80s. Okay. So here is a random internet prom picture, right? So this girl saying, "Get this guy off me." All right. Now, think about a prom. Here's my stereotypical view of a prom from, you know, perspective of someone from foreign land, right? So we have here the organizing committee, right? So it'll make sense as I discuss it, right? So we have this pair, we have this unlikely pair, right? We have, think about it, when you have a prom committee, you need a nerd, right? You need a nerd to do all the lighting, all the music, all the electronic stuff, right? All that nerdy stuff, you need a nerd, right? And then you need someone who's super popular to do the invitations and get people to come. So we have a nerd and a prom queen, right? What an unholy alliance that is, right? So the nerd and the prom queen have to get together to organize prom, right? So this is this compound BZ, okay? And they organize the prom, right? And then opening night comes, prom comes, and in comes captain of the football team, jock. He's Scottish, that's a joke, right? So when the jock sees the nerd with the cheerleader, what do you think happens? Well, nature happens, right? The more popular jock will replace, it's called a single replacement. I replace one from the pair, the nerd. And what we're left with, nature's balance is restored. The jock and the prom queen are together and the nerd's off by himself. Okay. Now in chemistry, it's kind of similar, but popularity is really reactivity. So if I look here, and don't worry about balancing numbers, I got hydrogen stuck to chlorine, less reactive, more reactive, right? So, sorry, more reactive, less reactive. So there's jock, there's the nerd, tin hooks up with chlorine, hydrogen's on its own, okay? So if we replace one from a pair, it's called a single replacement, okay? So single replacements are kind of interesting. I call them prom reactions, okay? Now what happens in high school does not reflect what happens in real life, okay? So, you know, the jock gets the nerd's girlfriend, so to speak, and then the nerd's off on his own. And then, you know, that nerd is Bill Gates, who founds Microsoft, becomes the richest person in the world, and then hires this person, has an affair with her, and the jock kills himself. That's a joke, right? But nerds will inherit the earth. Right, Leonard? Yes. Okay, so that's a single reaction, single replacement reaction, okay. Now next one, double replacement reaction, okay. Now this is just for your entertainment and learning, right? So I call this, and not to be repeated, right, but this is what I call a swinger reaction, right? So there's Oscar Paris, who famously has a license plate called Swinger, right? Okay, so we're going to do a lot of these things later. They're called double replacement reactions, right? I call them nicknamed swinger reactions, right? So here we are. in the next packet we'll see a lot of this, okay? So here's board middle-aged couple number 1, metal, non-metal, usually ionic, right? Here's board middle-aged couple number 2, all right? What do you do? Oh, here's an example. Throw your keys in the goldfish bowl, right? And then who do you go home with? The other one, right? So A goes home with Z and B goes home with X, all right? So they swap partners, get it? Swinger reaction, all right? Here's the most classic swinger reaction of all time. The silver nitrates hook up with the sodium chlorides, and this is who goes home together. Okay, I hope that makes sense, okay? So that's a kind of reaction. So when they swap partners, so we have 2 partnerships. When they swap partners, that's a double replacement. Okay, in the first one, it was called a single replacement because only one partnership was changed, right? Okay, here, both partnerships are changed. Okay, all right, so that's your double replacement. Finally, we have neutralization. Now, neutralization is not really a class of reaction by itself. It's kind of a subclass of double replacement. If you look, we have an acid, H plus on the front, doesn't matter what's on the back, with a base, plus on the front, doesn't matter what kind of plus, OH on the back. And then when I swap partners, the H will hook up with the OH to make water, and the metal will hook up with the non-metal to make what's called a salt, right? Remember, any plus and any minus is a salt, right? And that gives us a very important generic equation, right, which only applies to acid and base. So acid plus base makes salt plus water, and that's an equation you need to know, okay? So neutralization. Neutralization is something that's super acidic, super low pH, dissolves the metal maybe. With something super basic, something super caustic, also kind of dangerous too, like dissolves hair clogs, that's drain cleaner. Take these 2 very powerful chemicals, you mix them together, what do you make? Water. So it's a super important reaction, okay, neutralization. And it happens through a double replacement mechanism, so they just swap partners, okay? So HCl, NaOH, swap partners, Na hooks up with Cl, that's A salt, it's not always table salt, you know, it could be lithium chloride, right? And then H and OH makes H2O. I actually like to write, when we do this for real, I like to write water as HOH, because it kind of tells me where the parts came from. That's a nice little trick you can do later. Okay, so those are the 5 kinds of reactions which you'll be asked to recognize, okay? All right. Now, okay, I'm going to do my Danger Will Robinson thing. Now, balancing equations is always a 2-step process. I call it the chemistry benediction, right? So you go vertical, then horizontal. People who try and do 2 things at once will always get it wrong. I'm going to teach you 2-step process, right? This is step 1, okay? And in step 1, all you do is turn names into formulas, okay? It's not necessarily going to look right, okay? But that's okay. You just want to get the correct formula. So it's always formulas first, okay? So let's look at this one, all right? So let's make these very simple reactions. They're probably going to balance themselves because I chose simple ones, all right? But we'll see. Okay, so first things first, okay? So turn names to formulas. And then, you know, once we got them there, just tell me what kind of reaction that is. So sulfur, if it's an element, it's in the periodic table. You just choose the element name, right? Sulfur, or symbol S. It's told me it's a solid. So much like a single atom of carbon was CS in the block of carbon, single atom of sulfur in a match tip maybe. And this is what happens when you strike a match, right? That's the yellow stuff on the match tip. All right, so that's a sulfur atom in some solid sulfur, okay? With oxygen gas, we've seen this before. So I'm going names to formulas, turns into sulfur dioxide. Now you know how to turn molecular names to formulas, right? So 1 sulfur, 2 oxygens, there we go, sulfur dioxide. That's a self-balancing equation. 1 sulfur, 2 oxygens, 2 oxygens. There's no other work necessary to balance it, okay? What kind of reaction is that? Combustion or combination? A or B? A or B. All right, now, feel free to try these. I'm going to go through them, obviously, okay, but feel free to try them. Okay. Quick drink here. So, magnesium carbonate. Now, be careful. Anything with a metal in it's going to be ionic, right? So, magnesium, you know, if you want to put the charges underneath and erase them later, you can, but that's a +2, right? Carbonate, hopefully you remember, is also a 2, but a -2, all right? So that formula is good to go, all right? We didn't have to change the ratio of magnesium, which is an ion of +2, with carbonate, which is an ion of -2. It's good, all right? There we go. Turns into magnesium oxide, again, nice and easy, because magnesium's a +2, oxide's a -2. All right, if it was chloride, it'd be MgCl2, wouldn't it, right? But no, okay. So again, nice, easy one. And then carbon dioxide gas, we know that one there. So we've done names to formulas, names to formulas, names to formulas. It is actually another self-balancing. 1 magnesium, 3 oxygens, 1 carbon. All right, what kind of reaction is that? Well, I make more from less, so that's decomposition. Right. This one, interesting, okay, interesting. This one's a little bit more challenging, all right? So we got zinc, periodic table, nice easy one to start. Zinc solid is just like, you know, a metal, right? So it just uses its symbol from the periodic table. Now careful, copper 2 nitrate solution, right? Copper 2 nitrate solution. So copper 2, that's copper with a +2 charge. Now be careful, because nitrate is what charge? Remember? -1, right? So that's a -1. That's a +2 because it's copper 2 nitrate. So I need 2 of those, okay? Solution, dissolved, aqueous, right? So that's that state symbol aqueous we talked about briefly. So whenever you see solution, it's aqueous, all right? Turns into metallic copper. No, that's just copper. Cu. Cu is the symbol for copper. It's also a greeting in Scotland. It's a joke, but true. Plus, now zinc 2 nitrate, so zinc is a +2, nitrate's a -1, so we need 2 of them, solution, okay? Now if we count the atoms both sides, it's again self-balancing. We'll get more into balancing in a moment, but we're good. That's a jock, nerd, cheerleader. It's a single replacement. All right, now then, next one. I purposely didn't finish this, okay, purposely, right? Because it's an acid and a base, right? Makes salt plus water. So hydrochloric acid, I'm going to write it kind of backwards, right? HCl is hydrochloric acid, hope you remember that. Solution. Plus sodium hydroxide, +1, -1, hopefully you remember that. Now when I swap partners, it's a word equation, acid plus base makes salt plus water. The H and the OH will stick together to make water. I'll write it as HOH, you may write H2O, that just helps me count the number of ions, right? And then Na hooks up with Cl. And we know that's dissolvable. There we go. All right. Acid plus base makes salt plus water. Okay, so that's a neutralization. Fair enough. All right. Now, back in the day, really before Dalton's time, okay, so Dalton revisited the idea of atoms, okay. Before he came back with that idea, you know, before 1803, yeah, chemists had noticed one thing for every single equation, and that was the mass of the reactants equals the mass of the products, okay. So if I just think about that just for a second, it makes total sense. Look at this first one. This is a sulfur. If we look in the periodic table, it weighs 32. This is oxygen, 16, and another one 16. So the mass of these atoms is 32, 16, 16, 64, right? Over here, sure, they've rearranged, but it's the same number and type of atoms. So that's 32, 16, and 16. The mass of the reactants always equals the mass of the products because they have the same number and type of atoms as before, right? Okay, and no one really knew why that was true, so they just called it the law of conservation of mass. Mass of reactants equals mass of products. We now know why, all right, because I've got the same number and type of atoms. They don't lose weight from left to right, okay, they just rearrange themselves, okay. So that answers that question, okay. So why are the masses of the reactants equal to the mass of the products, which has been seen forever in chemistry? Because hey, it's the same number and type of atoms. So we don't have to go in and individually weigh things to balance an equation anymore. We just count the number of atoms both sides in our equation. If it's the same number and type both sides, it's balanced. So this one is balanced, 1 carbon, 2 oxygens, 2 oxygens. Yes, they're hooked up differently. That's chemistry, right? Chemistry is rearranging your atoms to make new materials, right? So that's a balanced equation. Okay, so we're going to work out balanced equations based on conservation of mass, it's technically called, but it's really the same number and type of atoms before and afterwards. Okay, in all the above, I chose these to be easy. They're all self-balancing, right? So we were practicing just turning names to formulas. To make the whole balancing work, we may have to change the number of things, which we'll put a number in front. We'll see that in a moment. Okay, now then, I said it was a two-step process, right? And this is where people always get it wrong, okay? But I'm here to fix that, okay? So, rules of balancing equations, okay? Now I'm about to run out of time, so I'm gonna kind of come back in a second. You know, I'll keep going with the same video. I just need to stop and come back, so see you in a second. Okay, so balancing is a two-step process. Step one, I call it the vertical step, names to formulas. So if I give you the names of things, just turn the names to formulas. And then step two is balancing to make sure the conservation of mass is obeyed, the same number and type of atoms. Okay, so here we go. So first things first, just what we said. Okay, construct an unbalanced equation, sometimes from a word equation. Once those formulas are down and they're correct, do not mess with the formula, okay? The formula of carbon dioxide is CO2, right? You can't change it once it's on the page. Yeah, it may not look right in terms of balancing, but you can't change the formula, okay? So, as Scotty says, right, can he change the laws of physics? You can't change the laws of chemistry either. So once the formula is established, you cannot change it, right? So let's see how many of you fall into the trap, okay? What I want you to do is step one, turn names into formulas. Turn names into formulas. Give you a second. Come on back. Names to formulas. Step one. Okay. Are you back? All right. So the unbalanced equation is magnesium solid plus oxygen gas turns into, how many of you wrote MgO2? Well, Mg plus O2 makes M. No, it doesn't. All right. Magnesium oxide has the formula magnesium plus 2, oxide minus 2. Yes, your brain's screaming at you. It's wrong, and your brain is correct. Okay. It's not yet balanced, but I can't change the rules of chemistry. Magnesium oxide has the formula MgO. Okay, so you can't do two things at once. You've got to do vertical first, which we've just done. Names to formulas, right? And then on the next page, I'll show you how you fix your brain, right? And say, hey, well, how can I make it right in terms of the same number and type of atoms, okay? So be super careful. All right, so step two, like I just said, right? Don't change the formulas. You can't, all right? So if I look at this, and let me show you the picture in a second, okay? Right now I've got one magnesium, one oxygen molecule, O2, and then one MgO, yeah? If I apply what I call the tennis approach, yeah, I can balance this, yeah? So if I look here, and just pretend to start, you know, you can put a 1 in front. We're going to change, if you've got a pencil, use a pencil, right? So if I look here, and this is what we're going to do right here, I've got one magnesium. It's nice to draw a little picture to start, right? One magnesium, one oxygen molecule. There's a better picture down here, which I'll show you in a second. All right, and one MgO, all right? Fair enough. Now, I've got to make sure the same number and type of atoms are before and afterwards. I can't appear or disappear atoms. No Harry Potter, right? One magnesium. Yes, it's hooked up to an O, but there's one magnesium here and one magnesium here. That's great. It's balanced with respect to magnesium. Just thinking about magnesium, it's balanced, right? Okay. Looking here, oxygen, O2, 2 oxygen atoms, right? Only one over here, so it's not balanced with oxygen, yeah? Okay, here's the trick, right? I can't change the formula. Many of you wanted to put a 2 there, didn't you? No such thing as MgO2, no such thing, all right? So how can I get 2 oxygens? Think of MgO like a car with 2 passengers, right? I can have another car with 2 passengers. Now I've got an O and an O. And if I do that, that's where the 2 comes from. So 2 means 2 cars, right? And there's 2 passengers per car, an Mg and an O. So I've got 2 oxygens now. Hey, great, I've got 2 oxygens. Fantastic. But what did I mess up? I've now also got 2 magnesiums. So we're going to have to throw it back over the net. Think of this as a net. We go backwards and forwards like a game of tennis. I've got 1 magnesium. What am I going to do? It's like a guy on a motorcycle, right? Well, for 2 guys, I need 2 guys on motorcycles. There we go. So 2 magnesium atoms plus 1 oxygen molecule makes 2 MgOs. 2 magnesiums, 2 oxygens. It's balanced. So you don't change the formula. Once they're down, you can't change them. You can put numbers in front now. I can have 2 vehicles, not 1 vehicle. We're good. Okay, so call that the tennis approach. 2 magnesiums, 1 oxygen molecule, 2 magnesium oxides, 2 Mgs, 2 Os. For the earlier ones, it's nice to draw pictures, okay? I really recommend that. It helps you kind of visualize the same number and type of atoms. So this is great, right? I love the microscopic view. Okay, so hopefully that's your first step into a much bigger world, right? We've done our first kind of true balanced chemical equation there, where we changed what's called the stoichiometric constant, or the balancing number. So the numbers in front are called stoichiometric constants, hence stoichiometry, or balancing numbers for simplicity. Right. Okay, now if we did this in lab, unfortunately we're not in lab, magnesium is used in fireworks a lot, right? It burns with a very bright white flame, okay? So there's my magnesium. Magnesium is a giant element, so that's a piece of magnesium ribbon there, some metal, right? So it's a giant arrangement of atoms, okay? Oxygen from the air, there they are, right? And then when we have a flame, what's actually happening in a flame? Flame's interesting, it's actually a plasma, right? So it's being atomized. So everything at that temperature is super hot. So it's turned into atoms, and sometimes electrons fly off to make ions. It's kind of like a plasma soup, if you like. And then in the flame, they're disassembled and reassembled, and it makes that magnesium oxide, which is kind of like a white powder. Okay. All right. All right. Now, it says work in small groups. Groups don't get any smaller than 1. Okay. So give this a shot. Now, maybe do the first one together, and you guys can have a go, right? Okay. We're going to write balanced equations for the following. Okay. Now here's a picture of the space shuttle, right? If you look at the space shuttle, there's this big tank right here, isn't there? There it is, right? That tank is split about 2 to 1 in terms of the volume inside, with liquid hydrogen and liquid oxygen. Okay. The space shuttle burns hydrogen with oxygen to make a flame coming out the back to provide thrust, right? Okay, and what comes out the back is water, or that temperature steam. Yeah, so the space shuttle is like a giant steam engine, if that makes sense. Okay, so what we're going to do is write a combustion reaction for hydrogen. Okay, combustion add oxygen. All right, and it kind of tells you what happens in the space shuttle here, right? So this is hydrogen is the formula. The combustion of hydrogen gas, right? So let's convert hydrogen gas, H2. Remember, hydrogen is a diatomic, okay? Everything in nature is stuck to other atoms apart from the noble gases, right? Either element or compound, right? Plus, this is step 1, names the formulas. Combustion, reacting with oxygen, right? There we go. Now I like to put a little kind of thing in front. Turns into water. Well, water will be steam at that temperature, so yeah, same formula, H2O, and then we'll put gas because it's hot, right? Okay, now, draw a little picture. 2 hydrogens stuck together, fair enough. 2 oxygens stuck together, fair enough. And then H stuck to O, stuck to H, right? Let's balance it. Just assume there's 1s in front, right? 2 hydrogens, 2 hydrogens. Right off the bat, it's balanced with respect to just thinking about hydrogen, right? Okay. However, 2 oxygens, 1 oxygen. Been waiting to say this all morning. Houston, we have a problem. Okay, so how are we going to fix that, right? So instead of having 2 water molecules which have only the 1 oxygen, right? Sorry, let me start. Instead of having 1 water molecule which has 1 oxygen, I need 2 water molecules. I can't change the formula, but I can have more than 1 formula, okay? So I need 2 oxygens. Each molecule has 1 oxygen, therefore I need 2 molecules, right? Okay, so 2 waters, 2 O's. So we're balanced with respect to oxygen, right? But what did I just mess up? Hydrogens, right? I got 4 hydrogens over here now, so I need 4 over here. I need another hydrogen molecule. Okay, so you can count them, right? So I got H2, and there's 2 of them, so that's 4 H's. 1 O2 is 2 O's. And then 2 H2O, 1, 2, 3, 4 hydrogens, and 1, 2 oxygens. So 2 oxygens were good, 4 hydrogens were good. It's balanced. Okay, all right. Now, whenever you combust something, as we mentioned, you make its oxide, right? So it's easy to write a word equation, right? So just burn something, you make its oxide, yeah? And if it's a metal, it's going to be an ionic product, right? So combustion of sodium, Na, solid, plus oxygen, you're tempted to write what? NaO2, aren't you? But it's not right, is it? Okay, think about it. What charge does sodium make? Group 1 makes +1, right? So that's going to be a +1 ion. Oxide makes -2. So I need 2 plus 1s to cancel the 1 minus 2. And they're always solids. Okay. All right. So that's our unbalanced equation. Of course, it's not balanced. Okay, it's not balanced. All right. Now here we might get some kind of rally going with the tennis, right? So we'll start with 1, right? So 1, 1, and 1. So let's kind of think about that. So, you know, you can use the pencil, which makes sense, right? So I've got 1 sodium here, and the vehicle contains 2 sodium passengers, if that makes sense. The formula has 2 sodiums in it, right? So I'm going to have to change that to 2. So now I've got 2 Na. You know, instead of drawing the pictures, you'll get used to just kind of writing the number of atoms underneath. So I've got 2 sodiums, I've got 2 sodiums. It's balanced with respect to sodium. But now look here, I've got 2 oxygens, right? And I've only got 1 oxygen. Now I can't cut the molecule in half, so I'm going to have 2 of these guys to get 2 oxygens. 2 oxygens. Fair enough, so I've got 2 oxygens, 2 oxygens. But now I've got 4 sodiums, right? I need 4 sodiums over here. There we go. Ah, now it works, all right? So 4 sodiums, 2 oxygens, 1 O2, 2 Na2Os, so that's Na2O is the vehicle, 2 vehicles, so, you know, 2 guys and a girl in the car, 2 cars, 4 guys get out, 2 girls get out, right? 2 oxygens, 4 sodiums. Okay, so the balancing numbers are 4, 1, 2. All right. Next one, very, very popular reaction, hint, hint, right? Popular with examiners, but kind of tricky because it's a single replacement. Single replacements are always a little tricky to balance, okay? And I'll show you a trick, okay? Now, dissolving, it should be reacting. Reacting of sodium metal, take sodium, and you react it with water. And I'm going to write water like this to give sodium hydroxide and hydrogen gas. Ah, there we go. So there's my unbalanced equation. Sodium metal, water, whichever it is, HOH, reacts with sodium hydroxide, NaOH. So later on, when we balance, I just count the number of hydroxides. It's like, you know, I don't count the individual oranges, I count the bags of oranges, right? So if the ion doesn't change formula left to right, I can just count the ions, right? Not the individual atoms. It would work if I counted atoms, but for ionic equations, just count the ions if they don't change formula, all right? Then the H2, 2 hydrogens stuck together. So let's do it. Now the trick is to kind of start with the one that looks the easiest, right? So sodium, yeah, 1 sodium, 1 sodium, good to go, right? Now we got H and OH, right? So there's my OH right there, right? Well, I've got 1 OH here, 1 OH here, fair enough, right? Then I got hydrogen, 1 hydrogen here, 2 stuck together here. Oh no, that's my source of hydrogen for this, so I need 2 of them. All right, so 2 hydrogens makes 1 H2, fair enough, all right? Then, because I've got 2 waters, I've got 2 OHs. There's my OH, so I need 2 of these. Okay, got 2 OHs, 2 OHs. Now I've got 2 sodiums. Now I've got 2 sodiums. There we go. That's balanced. 2, 2, 2, 1. Okay, that's a little bit of a tricky one. Okay, but if you write this as HOH, you can count OH ions instead of atoms. It works out. All right. Now, practice, practice, practice with these. That's what, you know, gets you good. All right. Now, let's talk about organic reactions. Okay, so organic reactions are reactions that feature organic molecules. What's an organic molecule? Well, an organic molecule contains carbon and hydrogen in any ratio. That's called a hydrocarbon. So methane, which we'll see in a second, ethane, propane, butane, you know, these kind of things, wax in candles, right? These are hydrocarbons. They're basically carbon and hydrogen stuck together, okay? Or I can have a carbohydrate, CXHYOZ. All right, so carbon, hydrogen, and oxygen stuck together, like sugar would be a carbohydrate or alcohol, right? Okay, that's called a carbohydrate. hydrate, and that's human fuel, right? Yeah, okay. All right. Now, when we combust something, we basically disassemble it, right? So when we burnt sodium, we took the piece of sodium metal, disassembled it into its atoms, and then added oxygen to the atoms to make sodium oxide, right? Okay, if that was aluminum, it would make aluminum oxide. So you're just adding oxygen to the atoms. All organics contain carbon and hydrogen, right? So when I burn anything with carbon and hydrogen, or carbon, hydrogen, and oxygen, because oxygen just helps it burn better, okay? What are you going to make? Well, carbon's going to make, when it burns, CO2, right? And hydrogen, when it burns, Space Shuttle, is going to make water. So we can write very simple questions for combustion of organics, right? So for example, the combustion of methane, yeah? Well, what are the products of combustion? Well, it's got carbon in it, so it's going to be carbon dioxide, hydrogen in it, so it's going to be water, okay? So for organics, you always make carbon dioxide and water as products. That's the trick, okay? Now, when you balance, as you can see, oxygen is everywhere, right? So we'll save oxygen till last. And always a good idea is to do the easiest thing first and the hardest thing last. So the thing that appears the least, try and balance first. The thing that appears the thing that appears the most, leave it till last. It will probably work out itself, okay? So if I like to think about, you know, formulas of carbohydrates like that. That's the order I'm going to balance as well, okay? So this is kind of a nice example because I've got a picture, right? So there's methane, CH4, right? There's oxygen, carbon dioxide, and water, okay? Maybe, instead of kind of looking at the sheet there and kind of cheating a little bit, let's balance it, right? So, combustion of methane. CH4 is methane, gas, plus combustion, oxygen, right? Turns into combustion. Well, carbon's going to make carbon dioxide, and hydrogen, when burnt, is going to make water. At that temperature, probably a gas, steam, right? Okay, start with ones everywhere. Now remember my trick. Start with carbon, then hydrogen, then oxygen, right? So how many carbons over here? One carbon here, right? So one molecule with one carbon passenger, one carbon on the left. Conservation of mass, same number and type of atoms over here. How many carbons on the right? Well, this is the only place it appears. I've got one molecule with one carbon passenger. So hey, one carbon, one carbon. We're balanced with respect to carbon. Hey, get it out of the way. Next, hydrogen. Well, here's methane, right? 4 hydrogens per vehicle, 4 passengers, so 4 hydrogens. None here, none here. Ah, there they are, right? So over here right now we have 2 hydrogens, but we need 4, right? So hey, 2 hydrogens per molecule. How many molecules do I need? 2. All right, so 1, 1, 1, 2 so far. Okay, we've balanced carbon, we've balanced hydrogen. We've saved oxygens till last, right? Now here's the trick. Because we have 1 carbon dioxide and 2 waters to balance carbon and hydrogen, we've locked in a certain amount of oxygen over here, right? So for carbon dioxide, which contains 1 carbon, we need 2 oxygens, right? So that's locked in too. For water is 1 oxygen per molecule, 2 molecules locked in there, so that's another 2. So we've got 4 oxygens locked in over here, if that makes sense, right? Because we already have to have 1 carbon dioxide and 2 waters to balance the other things, right? So I need 4 oxygens. That means I need 4 oxygens over here. Oh look, they travel in pairs, O2. So how many pairs make 4? 2. So it's 1, 2, 1, 2. All right, there it is. Okay. So organics, we can write deceptively simple questions, golden rule, balance them in order, carbon, hydrogen, oxygen. Oftentimes oxygen will take care of itself. All right, so let's do it again, right? So try this one, the combustion of ethanol. Well, bring it down. Try the combustion of ethanol. There's this kind of pseudo-structural formula. You'll see that in organic books sometimes. Try burning ethanol, right? Use the rules we just talked about. Now, there's a little bit of a twist. If you can get that twist, fantastic. Okay, try not to peek at the picture. All right, give it a shot. Okay, so let's do it. So, ethanol, CH3, CH2OH, right? Ethanol's a liquid. That's called vodka, right? Combustion. O2 gas, all right? Turns into, well, it has carbon, hydrogen, and oxygen. It's organic, okay? The oxygen will just help with combustion, so it's just burning carbon and hydrogen, right? So I get carbon dioxide when I burn carbon, and water when I burn the hydrogen, okay? All right, so that's my unbalanced equation, names to formulas, okay? Now, let's count. Carbons first, right? How many carbons over here? 1, 2, all right? So far, how many carbons over here? Well, just the one in the one molecule of CO2, but I need 2 carbons, right? So I'm going to have 2 molecules. Each molecule has 1 carbon. It's balanced with respect to carbon. Fantastic, right? How many hydrogens? Careful. 3, 4, 5, 6. 6 hydrogens. I need 6 hydrogens over here. Well, I got 1 water molecule so far. Each water molecule contains 2 hydrogens. Hey, how many things with 2 do I need to get 6? Well, that's 3, right? There we go. Now, here's a little trick. Hopefully you got this. How many oxygens have I locked in? Well, 2 per carbon dioxide and 2 molecules, that's 4, and then another 3 here, right? So that's 7 oxygens. Fair enough. I've locked in 7 over here. So I need 7 here. Here's where it's interesting, right? Because I've got 1 in there, and I've specified I need 1 molecule there, right? Okay, so I'm not going to write 7. I'm going to write 1 plus 6. There's the 1 I need extra for the passenger inside ethanol, right? That leaves me with 6. Oh, 2 times what is 6? 3. So it's 1, 3, 2, 3. Hopefully you saw that little trick there. Okay. All right. There's the picture. CH3, CH2OH. All right, so that's kind of a pseudo-structural formula. That's what it looks like in real life. Okay. So I've got an oxygen inside, right? 3 O2s, 2 CO2s, 3 waters. Let's count. 2 carbons, 1, 2, 1, 2. 1, 2, 3, 4, 5, 6 hydrogen. 1, 2, 3, 4, 5, 6 hydrogen. 1, 2, 3, 4, 5, 6, 7 oxygen. 1, 2, 3, 4, 5, 6, 7 oxygen. Works fantastic, right? Okay. All right. Now, if you really got this, you can do the sugar one, okay? So the combustion of sugar, that's glucose, right? So glucose, try and balance that one. You'll see the same trick we saw with the ethanol. You'll have to account for the kind of the oxygen inside over here when you do the balancing of oxygen at the end. But try it. If you can do this one, you're in good shape, okay? All right, pause, give it a shot. All right, you're back. So C6, H12O6. Let's call that a solid because it's sugar, right? Plus oxygen turns into CO2. It's organic, so we're burning carbon and hydrogen, right? Plus water. That's a liquid. Okay. So 6 carbons, we need 6 carbons. There we go, 6 CO2, right? 6 carbon, 6 carbon. 12 hydrogens. Well, they travel in pairs, so I need 6 water molecules. That's 12 hydrogens. Okay. So by balancing carbon, I got 6 CO2s. By balancing hydrogen, I got 6 water. So how many oxygens are locked in? 2 6s are 12, plus 6 is 18 oxygens. Fair enough. So I need 18 oxygens over here. Oh, look, there's 6 in there, right? So I'm going to write 18 as 6 plus 12. That's 18, right? So that takes care of my 6. 12. 2 times what? 6. There we go. All right. Hopefully that makes sense, yeah? Okay. So, recap. Be able to write balanced equation from a word description, okay? So remember, it's a 2-step process. Names to formulas, vertical, then balance, okay? 2-step process. Practice, practice, practice. Lots of questions in the book, right? Then, once you got your balanced equation, kind of a secondary issue, there are 5 kinds of chemical reactions. Be able to identify what kind it is, okay? Remember the golden rules of this? 2-step process, names to formulas, chemical benediction, vertical, names to formulas. What you write down doesn't look balanced sometimes, and that's okay, right? So names to formulas first. Once you've got the correct formula, do not mess with it, right? And then do the tennis thing, step 2 here, put balancing numbers, stoichiometric constants in front to obey the conservation of mass law, same number and type of atoms before and afterwards, okay? Never, never, ever change a formula to make it work, okay? All right, if you can do this one, quick review, try it, okay? So, let's make that extra credit. When will I make this due? Let's make it due on Thursday, which is Tuesday a day, 16th, 17th, 18th. Thursday, 18th. You should get this done by the end of Thursday night. If you do, just type out your balanced equation, email, usual thing for this. Okay. Now, practice, of course, makes perfect. Okay. This is, again, a very similar to what I gave you on the test practice question. Okay. So I'm going to give you on your next midterm a whole page of balancing, right? Okay. And here are some classic questions. Rather than go through it with you, I want you to kind of practice, right? So try this, and then you say to yourself, well, where's the answers? Turn over. There's the answers, okay? So try it, then look at your answers, and, try and talk to me in an office hour, or ask at the water cooler or the discussion area for this if you've got questions, okay? So it's all about practice until it's familiar. It's like riding a bike, right? Once you're familiar with it and you practice it a few times, it's kind of second nature. But that whole process you got to kind of do. All right. So you're on that learning curve. Practice and then check. Okay. Lots of questions in the back of the book. All right. Time's nearly up. It's a good time to stop. I'll see you next time. Here's the Nerd Fest. Engage.